Hello, everyone, and thank you for viewing our poster. My name is Nicholas Jones. Today we'll be discussing the thermal modeling of small Earth orbiting satellites and their environment.
Hello, my name is Kevin Wynn, and I'm going to go into some background information to provide some foundation for our research. Thermal modeling can prove to be a difficult issue among small Earth orbiting satellites. However, our research looks to simulate the thermal response of a small spacecraft in Earth's orbit to ensure operation in extreme conditions. By treating the spacecraft as a point mass, a time-varying differential equation can be derived involving the heat loads for Earth albedo, Earth IR, direct sunlight, and heat loss of space. This function, in combination with orbit geometry, allows for the hottest and coldest temperatures to be determined, along with how fast it takes to reach those temperatures.
The purpose of this research is to extend concepts beyond the standard curriculum to develop tools to conduct transient thermal analysis on spacecraft. This will involve extracting problem geometry from SDK and solving a transient point mass thermal analysis for a satellite. But first, we must define the thermal environment through parametric studies of different heat loads and design factors.
Hi, my name is William Sufa, and I worked on the albedo load versus altitude plot. Albedo is known as the sunlight reflected off of a planet's surface. For our graph, the albedo heat load was calculated as altitude increased at the subsolar point. As can be seen from the plot, as altitude increases, the albedo load on our satellite decreases. As we approach geosynchronous orbit, we see that the thermal load due to albedo is almost zero. This means that as we put our satellites closer to Earth, the reflectivity of the surface and the cloud coverage will be needed to be taken into consideration.
Hello, my name is Nathan Wagner, and I am presenting on the relationship between Earth IR and altitude. Earth IR is the thermal emission directly from our planet. This plot shows that as altitude increases, Earth IR decreases. As seen, Earth IR is nearly negligible for satellites in GEO, whereas satellites in LEO are impacted significantly. Given this, local conditions must be considered further in thermal analysis for satellites in LEO.
Hello, my name is Giacomo, and I was tasked with analyzing the steady-state temperature of the satellite. As described in these graphs, the warmest temperature the CubeSat experiences is approximately 295 Kelvin, with direct exposure to solar radiation, while the lowest is 160 Kelvin when it is in eclipse behind Earth. These results come from using 0.8 as the absorption and emissions coefficient. Depending on where the CubeSat is positioned during orbit, temperature fluctuates between 160 Kelvin and 295 Kelvin, with the goal being to keep the internal components of the CubeSat functional through these cycles of extreme heat transfer.
Of importance in determining the spacecraft thermal state is the spacecraft's ability to absorb and emit heat. This is described partially by the absorption and emission coefficients of the spacecraft surfaces. This chart compares the steady-state temperatures for a 1U CubeSat with a variety of emission and absorption coefficient combinations, and demonstrates a nearly 600 Kelvin difference between the most extreme combinations. This suggests the importance of choosing the appropriate surface finish for thermal control. To best exemplify this, coefficient regions of common spacecraft surface finishes are plotted over this chart.
Hello, this is Daniyal, and today I'll be discussing about cloud coverage. Cloud coverage plays an important factor in determining the temperature of the spacecraft. Two of the three main sources of the heat transfer for the satellite, albedo and Earth's IR, heavily rely on how cloudy the Earth is. Our albedo will increase if there are more clouds present, as the clouds will reflect of the solar beams back to the spacecraft, creating a mirror effect. On the other hand, Earth's IR is inversely proportional to the cloud coverage. The graph on the right captures the spacecraft temperature based on the minimum and maximum cloud coverage, where the x-axis is the time in hours. If it is an extremely cloudy day, then the spacecraft will reach a maximum temperature for almost 310 Kelvin, where during a nice and sunny day with less clouds, the maximum temperature will be around 280 K. Now, this is almost a 30 Kelvin change, which is sufficient enough to melt some of the components if we are not careful enough. In conclusion, the clouds coverage plays a crucial role in understanding the thermal environment of the satellite.
Hello, my name is Cody and I will be discussing the transient thermal analysis. So piecing this information together, we can form a rudimentary thermal model of a general cube satellite. Here we have an expanded graph for a low Earth orbit, which shows the different effects on the satellite's temperature. As the satellite moves into the view of the sun, there is a discrete jump in solar radiation and an increase in albedo. Then conversely, during this time, There's a loss of heat due to infrared radiation in the surrounding temperature of space because of the increasing temperature of the spacecraft. And this has overall result of heating the spacecraft. And then as the satellite moves back towards the shaded region, the albedo begins to decrease again, and the satellite's temperature begins to level off and then drop. Then after the satellite moves back into Earth shadow, the satellite begins to cool rapidly. And then here we have 3 different orbits graphed against each other, those being low Earth orbit, geostationary orbit, and a highly elliptical Monaya orbit. You can see how drastically the temperatures can differ over time depending on each orbit. The temperature fluctuation for low Earth orbit happens much more frequently, but for the Monaya and geostationary orbit, the fluctuations happen over a much greater span of time. And for the geostationary Monaya orbit, it also reaches much more drastic temperatures, the Monaya reaching roughly around 300 Kelvin at points, and the geostationary dropping to roughly 110 Kelvin. So keeping track of these maximum and minimum achieved temperatures, as well as the rate at which the temperatures change, is vital in the development for the onboard systems and the structural design of the satellite as a whole.
Future versions of this work will focus on further integration with STK to provide higher fidelity modeling of the spacecraft attitude and the environment geometry. We're also looking to integrate with ANSYS to enable the use of higher fidelity spacecraft models. A long-term goal is to be able to use this analysis to design the thermal control systems for future CubeSat missions. We'd like to take the opportunity to thank Dr. Keven Schrader for his support and guidance throughout this semester, and I'd like to thank all of you for coming out to view our poster.